Okay, so good afternoon. Let's look at what we call software-defined network. We're just having an overview. So Owen, help us with the objectives.
Upon completion of this section, you'll be able to be familiar with the benefits of SDN,
yes,
master the SDN concept and architecture, understand SDN evolution for traditional networks.
Exactly. Okay. So we're going to look at SDN in terms of the concept and architecture, benefits, and ways in which it is implemented. Now, data control and forwarding on traditional networks. So traditional networks distribute control architecture, where each device has an independent control and data planes. Now, generally, each router in a traditional network has a control and data plane. The control plane is responsible for protocol computing, so for calculating the protocols in order to get the best route. Data plane, on the other hand, is used to forward, is actually responsible for forwarding packets. So in traditional networks, this is actually implemented on the same device. Now, as you can see, each device has a control plane and a data plane. So the control plane is used to calculate the routes, put them on the routing table, and then they are forwarded to the data plane. Now, the data plane, packets are now forwarded using what we call the forwarding information base, FIB. So that is how traditional networks actually process route information and how they also forward packets. Now, the disadvantage with this kind of model is that routes cannot be calculated on all the devices from a global perspective. Reason being, each device independently collects network information and calculates its own route. So kila mtu anajikalkulatia, kila mtu anacalculate kulingana na the protocol that it's using. So the problem with that is that it cannot have a global perspective of the routes and the interconnection between the other routers. Now, the traditional architecture has 3 planes, what we call the management plane, the control plane, which we've already talked about, and also the data plane. Now, the management plane is used for managing the network, and normally you have a network management device that then communicates with the network equipment using a protocol called SNMP. I think this is one topic that we covered earlier. As we've said, on the control plane, then you're using protocols to calculate routes. Then the best routes are installed and are used to forward data packets from the FIB, or the forwarding information base, which is the forwarding table on the data plane. So really, a forwarding table will look something like this. So every router independently calculates and generates its forwarding table. So the network and the next hop. So that when you receive a packet, you know that, hey, if I receive a packet from this network, then I'm supposed to forward it out to this particular guy. So really, that is what happens. These are called NMS clients, network management system clients. They are the devices that you're using as the network administrator to monitor the network. So you're monitoring the network on the management plane. So of course, we know that the management plane provides services such as performance monitoring, just to look at the state of your network, and also can be able to generate alarms in case anything goes wrong, or in case we have congestion on your network, and so on and so forth. So really, that is the purpose of the management plane on the traditional network architecture. Now, what are some of the limitations of this kind of traditional networks? The first problem is inflexibility in traffic path adjustment. We just said that because everyone calculates independently their routes, then you cannot have a global picture of the entire network segment. So if you want to then do traffic path adjustment, we actually learned about this in the previous module, and we saw that it is really complex. It is really complex to do traffic engineering on traditional networks, because you have to do it hop by hop on each router most of the time. And it can be time consuming, prone to errors, especially on larger scale networks. So those are some of the problems with traditional networks. So inflexibility in traffic path adjustment. The other one is complex protocol implementation and operation and management. So again, traditional networks use complex protocols such as BGP, MPLS, OSPF, ISIS, VRRP, etc., etc. So you see, there are quite many, and most of the time, again, you have to configure in all the network equipment that you need to use that particular protocol. So it can also be very strenuous. So complex protocol implementation and operation and maintenance. The other one is slow service updates. So on a new on a traditional network, it can take a long time to deploy a new function. This is because the control planes of the network devices are closed, and the devices from the different vendors may be using, for example, different control mechanisms. So it's really a problem. For example, if you want to incorporate a new router into this particular network architecture, so it really is involving, because of even these other two disadvantages. So slow service updates. Additionally, software upgrades need to be performed on every device, which also greatly reduces what we call the work efficiency. So those are some of the problems with slow service updates. Now, let's look at now SDN, or software-defined network. Software-defined networks is a concept that was proposed in 2006 by Professor Nick of Stanford University and his team. So they brought out a concept called OpenFlow. OpenFlow concept, and used this technology to implement network programmability, which triggered the advent of SDN. So the three major features of SDN is, number one, SDN will separate the forwarding and the control plane. We already know what the control and the forwarding plane does. So really, the first thing it does is to separate those two. Now, after separating them, actually what happens is that every router will have their own forwarding plane, but they'll share a common control plane. So that common control plane is what you're calling the centralized control plane. So the controller centrally manages network elements and delivers flow tables. That means that protocols and their calculation are actually implemented on what we call the SDN device. Then the other feature for SDN is what we call open interfaces. Now, to deploy third-party applications, you only need to program new network functions using the open interfaces provided by the controller. Then you can run the functions on the controller. So it also increases the deployment of new services within your network, and also promotes interoperability between devices from different vendors, for example. Now, it is important to note that an SDN is not a network management system nor a planning tool. No, it is not. Why? Because an NMS does not separate control and forwarding planes, and a planning tool is used for different purposes than that of a controller. Okay, so now let's look at this architecture. So the SDN network architecture is actually a 3-layer architecture. So the first layer is called the orchestration and application layer, and then we have the control layer and the forwarding layer. Now, the orchestration and application layer consists of application programs that are used to meet service requirements for the users. And normally, what is happening here is this is your controller, and the controller can just be a server. So you have a machine which you are using to program the controller. So they'll communicate via an application programming interface. So that particular application that you're using to program the controller is on what we call the orchestration and application layer. Okay, then at the center of this, we have the control layer. So the control layer is where you have the SDN controller. The SDN controller, as you can see it here. And normally, the SDN controller will communicate with other network equipment by using the OpenFlow standard. Then at the bottom, we have the forwarding layer. So this is where your network equipment are, and now they're simply used for forwarding data, but not calculating paths and so on and so forth, because that is done at the controller. So I hope that is clear. Then the other thing you must understand is about the SDN interfaces. The SDN interfaces. Now, we have 3 types of interfaces, what we call northbound, southbound, and we have east-west bound interfaces. So those are the 3 types of interfaces. Generally, the interface that connects to your application from the SDN controller is what we call the northbound. Northbound interface. It uses RESTful APIs to communicate between your machine and the controller. Then southbound. So north, because of the compass, we know that the compass looks like this. So we have north, we have south, then we have east-west, something like that. These interfaces that are connecting to the forwarders is what we call the southbound. The southbound interface. To communicate with the forwarders, we can either use the OpenFlow standard, or we can use protocols such as BGP, PCEP, or NetConf. So all these are protocols that can be able to be configured in order to enable this network equipment to communicate with the controller. Then lastly, we have the east-west bound interface. This particular interface every SDN controller must have this particular interface. It enables the SDN controller to provide new services through simple modification or upgrade of the controller programs. East-west bound protocols also provide interfaces for cross-regional SDN controller interconnection and hierarchical controller deployment. What that means is that through the east-west bound controller, you can actually also be able to interconnect with other controllers. You can be able to interconnect with other controllers via the east-west. So that's why it's called east-west bound interfaces. So generally, those are the three types of interfaces that the SDN provides. The SDN working principle, sorry. So the controller here simply acts as a server. It acts as a server. Then on your network equipment, so you're having here the forwarders. So these are the forwarders. They're the ones that are used to forward traffic. You can also connect to your controller via an application on the application layer, so that you can be able to see topology, configure traffic paths, and so on and so forth. Now, what happens is that once you have a controller on your network that is communicating to the devices via, for example, OpenFlow, then these devices are going to send what we call register messages. These register messages are going to describe things like their interface ID, the VLAN the interface belongs to, or even vendor-defined information, such as the device type, the version number, the device ID, etc., etc. So the controller collects such information for local search and driver program loading. So that is why that information is important to the controller. So the controller will then collect topology information. So as you can see here, we are just using either SNMP or NetStream to pass information about the topology to the controller. So once the controller has such details, then it can be able to calculate proper paths based on the network resources, and it can also be able to deliver the flow tables. So that is how then this controller is able to, for example, determine this path here. This path here. Okay. So just to mention this again, network element resource information collection. So the controller must collect details about these devices. So information such as the forwarder registration information, resource report process, MPLS labels, VLAN resources, interfaces that particular guy have. It will also collect topology information using the different nodes, interfaces, and protocols. And lastly, it will now create specific paths. So switching route generation in SDN network. So the OpenFlow idea and functions. So the first time we're meeting this word flow. Flow or a data flow is simply a group of packets that has the same characteristics or same properties. For example, based on the 5 tuple, like the source IP address, the destination IP address, and so on and so forth. Now, the OpenFlow protocol is a control protocol that is used between the controller and the forwarders. So in traditional networks, we have the control and the forwarder and the forwarding being done on each device. But now here, with OpenFlow, we are simply separating. The control and the forwarding so that we can centralize. The control plane at the controller. Then these are your network equipment like the routers. So OpenFlow really enables now this intercommunication between the control plane and the forwarding plane, between the controller and your network equipment. Now, two roles. So one of the roles is for OpenFlow is what we call the OpenFlow controller. So this one controls OpenFlow switches, calculates paths, maintains network or device states, and delivers flow rules to OpenFlow switches. So when you talk of OpenFlow switches, we don't just mean switches, but also routers. Then you have an OpenFlow switch, accept instructions and flow information from the OpenFlow controller and returns state information. So OpenFlow switches forward and process data based on the flow tables and the flow rules. So this equipment do not actually calculate routes. The calculation is done by the OpenFlow controller. So that is how the OpenFlow actually implements that. So here we are looking at the OpenFlow network switching model. So this model simplifies underlying data communication. So switches and routers, defines an open public application programming interface for flow tables, and uses a controller to control the entire network. So what you're seeing here is that we have a controller. We are using the OpenFlow protocol to manage our devices. So for example, we call them OpenFlow switches, and we are able to pick details and also be able to give them what we call the flow table. So let's move on and look at the benefits of SDN. So that's centralized control and programmability. What benefits does it bring up? So number one, accelerating network service innovation. So because you can program the controller, so programmability and openness of SDN accelerate service development and innovation. So you can be able to do a lot. New services can be quickly provisioned through software programming. So from the controller, you can be able to do many things, including programming paths and many other intelligent stuff. So that is one of the advantages of SDN. The other one is simplifying networks. So the SDN architecture simplifies networks, removes the need for many IETF protocols. So using fewer protocols on a network also reduces difficulties in learning and lowers the network operation and maintenance cost. So this improves the service deployment efficiency. So these are the benefits of centralized control and separate control and forwarding in the SDN network architecture. So by implementing the controller, then it becomes easy to maintain your network because you don't have to configure all the devices, and it also improves the time with which it takes to add a new device on your network. So the other one is allowing for what we call white box devices. So what does this mean? In your network, we have two ways in which you can deploy devices. One of them is commonly referred to as vertical integration, and the other one is referred to as horizontal integration. Now, with vertical integration, one vendor, for example, Huawei, will provide the software, the hardware, and the services. So one vendor will provide everything, literally speaking. On the other hand, horizontal integration is a model where each vendor provides a component of a product. So you're not providing the entire thing, but just a single component. Then an integrator integrates all components and sells that particular device. So we have vertical, where we are using everything from the same vendor, and here where we are using multi-vendor stuff, then integrate them. So what do we mean then, allowing for white box devices? So in the SDN architecture, using the white box network devices, white box network devices really means devices from different vendors will be possible if the interfaces used between controllers and forwarders, such as OpenFlow protocol, are standardized. So this is going to be easier to integrate devices from different vendors. So by then, there will be vendors dedicated to OpenFlow forwarding chips or controllers. And also, the development model will change from a vertical integration, where you need to implement everything from the same vendor, to horizontal integration, where you can be able to take stuff from different people. So the SDN industry chain, so we have chip manufacturers that are called Centec networks, and also Broadcom. So there's some of the people who do SDN chip manufacturer. Network equipment vendors, of course, we have Huawei, Cisco, Ericsson, Alcatel, Juniper, etc. IT supplier for services, IBM and HP. And we also have certain innovation companies such as Big Switch that are used for creating virtualization of, for example, Nisira. Nisira takes a lead. It's a vSwitch based network virtualization platform, serving companies such as AT&T, eBay, Fidelity, Rackspace, etc., etc. So that is it about the SDN industry chain. So service automation. In the SDN architecture, the controller controls the entire network. So we've already said this many times. The SDN controller automatically completes deployment of services such as layer 2 VPN, layer 3 VPN, and shields specific internal implementations, thereby enabling network services automation without the need for any other systems. So in traditional, every device has its own control and forwarding plane, and they calculate their routes independently. Here, we have a centralized control plane, and it is this guy that does the calculation and share the flow tables to the individual routers. So it becomes possible then to automate many aspects of the network through the controller. The other big benefit of SDN is traffic path optimization. On traditional networks, optimal paths are selected for traffic by routing protocols, or we can actually configure traffic paths. However, the optimal paths may be congested. The optimal path may be congested. So whereas other paths are left idle. So on an SDN network, the SDN controller intelligently adjusts traffic paths based on traffic loads, thereby improving the network resource utilization. So what does that mean? On traditional networks, we are not able to determine after we've decided the optimal path, we are not able to determine whether the path is congested. We cannot be able, because we don't have a global view. But when you're using a centralized controller, then you're able to see the entire network, and you're able to see links that are idle and links that are congested. And therefore, you can intelligently adjust the traffic path then based on this information, and so that packets are then forwarded via paths that are less congested. So that is one of the biggest advantages of a centralized controller, and SDN for that matter. So ways of implementation for SDN. So we have the controller here. We have the controller here. We have the forwarders. And of course, we have, for example, your machine that you're using to program the controller. So what happens is that in your network, here we are using an example. It's called Tencent. It's just a company. So in your network, you have traffic monitoring systems. So these traffic monitoring systems are able to alert your machine. Then the machine is able to communicate now with the controller. Now the controller, Tencent Systems, collects LSPs, traffic statistics, and delivers traffic optimization policies, or LSP customization requirements, to the SDN controller. So your device then, after collecting, as you can see what it's doing here, it's simply collecting all those statistics from the network. Now, once the statistics are provided to the SDN, then the SDN controller optimizes traffic paths based on the network resource usage by creating what we call, by using what we call PCE, or path computing, is it element or something, path computing something, I'm forgetting. So that is how then the SDN is able to calculate. So this is one way in which you can deploy SDN. SDN Evolution for only the fabric means to implement centralized control for path calculation on the fabric network in the local domain. Okay. So the other way is what we call service only. SDN Evolution for service only. So for example, in data centers, you have what you call service chain model. So for example, if you're having a system here, and then you might have many tenants inside it, just meaning that they're the different services that you're providing. For example, forwarding, deep packet inspection, WAN acceleration, etc. So with this kind of architecture, you can be able to implement SDN controller to manage the provisioning of these particular services to your customers. So a unified VAS resource pool is deployed. The SDN controller implements service chain orchestration, centralized control and management, and VAS resource sharing. So really, here you're using the controller not really to control the network, but to control the provisioning of these particular services in your data center. So that is what is happening here. So that's the end of this particular chapter. Please take some time and go through these particular questions If you have an issue, you can let me know. Any questions? Okay, sawa sawa, asanteni.